So back in the derivative rules, we're going to look at these three, right? Sine, cosine, and tangent. And sine and cosine are kind of interesting because when you take the derivative of one, it becomes the other one, right? So you can see that when you do the derivative of sine, it just becomes cosine. That's like the easiest, one of the easiest derivatives you should know. Sine just becomes cosine. Cosine does the same thing, but it's got a negative sign with it, right? See that? So that's the thing you got to kind of be careful about. Sine changes right into cosine when you take the derivative, but cosine changes into minus sine. And then tangent becomes secant squared, also not too bad. So we're just going to look at this next one, and it's really pretty straightforward, I think, when you kind of think about those three things. And so if this is our f, then f prime is very simply 2 cosine x, right? Sine changes into cosine, no big deal. Cosine becomes minus sine, so it's going to be, maybe I'll write out the details. It's like plus 4 times minus sine. And then tangent turns into secant squared, so just minus 8 secant squared. And so the plus in between the cosine and the sine becomes a minus, is what I was trying to allude to here. Sine and cosine are ones that kind of come up a decent amount. Tangent we don't see particularly in our class, but it's one just to know, just to have an idea of moving forward. Yeah. Okay. Big deal. So sine turning into cosine and vice versa implies that the rate of change of sine at any point is equivalent to the value at cosine, which is kind of interesting, and vice versa. Right? So not only do they have their own function, but their function values describe the rate of change of the other one. It's kind of an interesting relationship. Natural log is another one that's not too terrible. Let's see here. So let me delete some of those things. Natural log, when you take the derivative of natural log, it just becomes 1 over x. So natural log of x, you got the x inside there. You just drop the natural log and do 1 over that. It's kind of an interesting one that has some interesting applications in the chain rule. So when we look at this one in the context of the chain rule, which we'll probably get to next week, some interesting things happen. In this particular one, though, we're just doing kind of a simple application here. And so if this is the one we're looking at, this becomes 1 over x. Right, and then the 9 is just a constant, and so that just becomes 0.
So I thought the 14 equals 0 was part of the natural log.
So it's multiplying the natural log, right? And so when we're thinking about the derivative rules, that's this kind of situation. Right, when you have a constant in front of a function and you take the derivative, the constant just comes along for the ride. Right, and then you just kind of take the derivative of the thing with the x in it. See that? So yeah, the reason that the 9 goes away, so let's just look at that again. Right, the reason that the 9 becomes a 0 is because there's a plus there, right? And so it's like its own thing. And so that becomes a 0 because when you take the derivative of a constant, we get 0. That we have that rule. But the 14 is multiplying, and so it's the constant multiple rule. Yeah, other good thought there. Other clarificational things? Is that okay? And so if we wanted, we could just write this a little bit simpler. Not a big deal, but this is also written as 14 over x. Right, no problem. Either one of those is fine. Okay. Just kind of leave it there. There are a couple other trig rules in here. If you just kind of notice. Sometimes I write them down. Sometimes I do another example. Like there's secant and cosecant, for example, here. These kind of have funky rules, the ones I'm highlighting. They honestly just don't come up a whole lot, and you have the rules if you ever need them, and so I'm going to kind of skip on that. Okay. What we really want to do, what I'd like to do today is move into these more complicated ones, these product rules, right? We got the quotient rule. These are the ones that are starting to get into real functions that we might actually see in practice. So I just want to stop real quick. Are there questions about either of these or anything else before we keep going? Just want to make sure everyone's with me before we leave anyone behind or anything. Okay. All right. Okay. So the product rule, let's go back to the derivative rules. So we're starting to get into these ones right here. Product rule, quotient rule, chain rule. And these rules oftentimes use the ones above it. And so the product rule tells us what to do when things are being multiplied. Right, let me just go ahead and be clear about how each one of these apply. Right, the product rule is for multiplication. Right, the word product means multiply. The quotient rule is for things being divided. When you can see that's the form there. And the chain rule, that's kind of the funky one. That's the hardest one usually. That's for composite functions. Notice how in this chain rule example, there's a G inside the F. And we've been looking at that notation a decent amount already with like F of X plus H, that's like that kind of thing. And I harp on that a lot in pre-calc too. So if you had me last semester, that might look familiar too. Okay, so these are the kind of things that we're going to walk through. My guess is today we'll get through at least product rule, possibly quotient rule. We'll see how it goes. Questions? Need to check this message. All right. All right, let's do an example. So notice how all the ones under the product rule situation, you have two things being multiplied. So let me throw in some multiplication signs, right? So I just throw a red dot in between those two things because it's like one thing on the left times one thing on the right, right? The thing in the middle here, it's cosine times e to the x. I'm just trying to write in some multiplication signs. And then in the third one, we've got natural log times y squared, right? So we're multiplying two functions in each one of those cases. And so it's very much an application of the product rule. And so when we're looking, let me zoom in on this one. It's like, this is our f function, and we're multiplying it by this g function. And when we think about it like that, we want to use the product rule. That's not product. With those two things as our f and our g. And so I'm going to try to do at least the first one very, very carefully. I'll write out all the details and then maybe not write as many details moving forward. So if we wanted to do this one, we want to use the product rule. It's going to be this. So let's just review what the product rule says, right? It says when you want to take the derivative of two things being multiplied, you look at the first one and notice how you take the derivative of it right here, but not here. Right, so we've got the derivative on the first one, but not the second one. And then with g, we don't take the derivative and we do take the derivative, right? So sometimes you write this, or I'll refer to this as f prime g plus f g prime, right? The derivative of f times not doing anything to g plus not doing anything to f times the derivative of g. That's what that says right there. And so I'm going to write that out. I'm going to do the details of that. Let me know if this looks okay. So this becomes, we're going to do the derivative of the first function, leave the second function alone, plus leave the first function alone times the derivative of the second function. And I don't want to keep clicking back and forth. It'd be a good idea if you had those rules out so you can kind of refer to it. But you see how this is like, right, this is my f prime g, f g prime. do you think? How's that look? Can I clarify something? We haven't done it yet, right? I'm just kind of setting it up, right? So when I write d over dy, that means I'm about to take the derivative, right? So like in this spot right here, we got to take the derivative, and then right here, we need to take the derivative. And so those require other rules, right? So we're kind of building on our rules. What rule are both of those things? They're both polynomials. And so what do we do on polynomials? What rule is that? It's the one that's in the homework for this week, the easy one. Yeah, these ones are just power rules. Right, you just have stuff raised to powers. And technically the constant rule too, right? There's some constants in there, like the 8's gonna go away. But mainly it's a power rule thing, right? And then so then we just do those power rules, and that's the answer. So let me do those power rules. Do we want to see the details of those power rules still? How many? I'll just do the details just in case people are still confused by that. So we bring down the power, multiply, subtract 1 off the power, right? So it ends up being 2 times 3 to the y to the 3 minus 1, and then 6 times 1 times y to the 1 minus 1. This might be the last time I do the details on the power rule. So let me know if you want to hear about that. Right, and then that other power rule, bring down the 1, subtract 1 off the power, and then the 8 just goes away. And so this will be our answer then, right? We'll get 6y squared minus 6 Thoughts on that one? Power rule? What do you think?
Would simplify it further?
Yeah, thank you for that question. So the question for people remote, do we want to simplify that at all? We could FOIL that out if you really wanted to. That's not the point of this problem, right? The point of the problem is we're doing calculus. Do you understand the rules? Do you understand the power rule? I would prefer you leave it like that, honestly, because it's just going to waste your time. If you multiply it out, that means I need to multiply it out to check it. That's not the point. So usually on a test and things like that, I will put in bold words, do not simplify. That's not the point of what we're trying to do here. John? Yeah, sorry, I left out the y. Thank you. Does everyone see that? There should be a y right here. I left out this y. I was just trying to copy down the thing on top of it. Yeah, so I just left that y off. So, okay, and then like on this one, sometimes you have a question about this, right? When you do y to the 0, that's just 1. And so it's like 18 times 1, so it just stays 18, right? In other words, when you take the derivative of just a variable, it just goes away. It becomes the number 1. Other thoughts, other questions, clarifying things? Thank you for that. Keep it coming. Anything in the chat? Nope. Yeah, so again, don't simplify it. That's not the point here. We're just trying to get down to here. You know, if this is part of a problem and then we wanted to use the derivative, like sometimes you want to find the max or something like that, then we might want to do some more algebra and things like that. But if we're just taking the derivative, the goal here is just to show me you know the derivative rules. Just leave it like that.
My paper, I just got the last
one. On a test, I would be okay if you felt like you could just write the last one down. I'm somewhat hesitant to say that because if it's like way off, I can't give you partial credit is sort of what I'm thinking. So if you feel very, very confident and you're in person and I know you're not cheating and all that, then I'm okay if you just kind of jump to the answer, especially on sort of a more simple one like this, I would call. But just know it's hard to give partial credit for wrong answers when it's just the wrong answer. Okay. I'm probably going to leave that middle one for you. It actually doesn't really matter. I'll do the next one and then I'll ask you to try the last one there. So it's another product rule, right? And we have, this is our F, this is our G. And these are now kind of they're not power rules, but we have rules for these ones. We just learned the cosine one, and e to the x is one we learned last time, but let me just remind you what that one is. E to the x just stays the same. Remember that? It's kind of funky. This is the e to the x rule. When you take the derivative of e to the x, it just stays e to the x. It's the best derivative rule out there. And so if we were going to do this one, we're going to do f prime g plus fg prime, right? So the derivative is going to be, I want to write the details, I've got room. So we're going to do the derivative of cosine, that's f prime. Leave g alone. Leave the f alone. Do the derivative of the g. Oops, that shouldn't be a plus though. That should be a multiplication. And e to the x just stays the same. So that that right-hand half, the second half of that is just literally just a copy of the original function. But cosine, we just learned, changed to minus sign. So this is a not too bad one. That would be it. F prime g plus fg prime. Look all right? Questions about how to follow that rule? You know, a lot of these rules, I know I've said this, but a lot of the rules are just understanding what the rule is telling you to do and then identifying the parts in the problem you're working with, right? Like, where's the F and the G? What do I do with those in the rule, right? That's what most of these rules are about. If there aren't questions, I was going to ask you to give this one a go. No questions? All right, try that one. So there's very clearly two things being multiplied here again. And so you just do the product rule one more time. And again, we've just learned both these rules. We learned ln becomes 1 over y. Y squared is going to be a power rule. While you're working on that, I'm just going to kind of slowly write the answer down. I'll do the details again. What do you do with that negative sign in front of the ln? Does that like mean anything? Sometimes people get. Yeah, it's just like a -1 coefficient kind of thing. All right, so you want to think about minus ln y as being like -1 times ln y. So it just stays out in front. Doesn't really change anything. It's a constant coefficient. All right, so ln becomes 1 over y. We just learned that one. And the 2y is a power rule, right? So this just becomes, excuse me, minus 1 over y times y squared plus, or really it's a minus because there's a minus sign there. So I'm going to change it into a minus. And we could simplify that, but I'm just not going to. It's not the point. Right? In other words, on the right here, sometimes people get a little frustrated by this. You could write this as y squared over y, which is just minus y. That's fine if you want to simplify that. I'm just trying to avoid these unnecessary extra steps. I clarify anything about the power rule? Is that right? as is always the case in math, we're just building on this stuff, but it's particularly important with these rules, right? Because we have these kind of basic rules like the power rule and the sine and the cosine, the exponential, and then these are going to be inside more complicated rules. And sometimes you have complicated rules inside of complicated rules with minor rules inside of them. So I'm just trying to emphasize, like, we really want to be keeping up, or else it's just going to get really confusing. All right, is that okay? The quotient rule is next, and it's worse. It's a little bit worse in a good way. I don't know, is that possible? So the quotient rule tells us what to do when we have fractions. We have not fractions, but rational functions, not technically rational functions. When we have two functions that are being divided, I should have just stuck with that. Right, we've got two functions being divided, like the next couple on the page. Here's how you take the derivative. And so it's really ugly looking, right? And notice how the numerator actually looks kind of like the product rule, where you're like doing the derivative of one, not doing it on the other one, and then the opposite, except there's a minus between them. Oops. So this is something people always forget. They sort of think like, oh, the numerator is the same as the power rule. Notice how there's a minus here and there's a plus here. So you've got to have the minus sign in the right place. That's kind of an important difference. And then the other main difference, which is hopefully staring you in the face, is that there's a denominator, obviously, which is just taking the denominator in the original and squaring it. So you don't like do anything to it, you just square whatever was down there. It's a really funky kind of rule. But fractions are complicated, and so hopefully it's not too surprising that when you take the derivative of a fraction, it's kind of a pain. So anyway, let's just keep that in mind. So keep that out. I'll maybe flip back over there, but let's look at this one. And we want to use the quotient rule. So here, we're going to use the quotient rule. And again, we want to identify in the rule, what's the f and the g? And so we're going to use the quotient rule with f being the numerator, so that entire top. And g is just the entire bottom. And so yeah, the numerator is itself the sum of two things. But the point is, when we look at the rule, f is the entire numerator, right? Whatever's in the top, we just say it's f. And then we just use the formula, right? F prime g minus f g prime all over g squared. Sometimes it's not too bad. Sometimes it's really annoying. We're not going to simplify it. That's not the point. So let's go ahead and write this one down. I'll probably just do this one and ask you to try the next one. So the derivative should have room to write the details. We're going to do f prime g. So that's going to be the derivative of the top times the bottom minus, don't do anything to the top, and then take the derivative of the bottom. All over the bottom squared. I've got my f prime g, f g prime. I'll highlight the minus sign. And then on the bottom, I've got my g squared. We got to take the derivatives, right? We got to do the f prime, we got to do the g prime. We're not going to simplify things. And we haven't seen secant yet, so we'll switch back over there. But does that look okay? Just kind of referencing the formula. So secant's one of those funky ones. Secant, right here, you can see it becomes secant tangent. So you kind of like copy it over and then also multiply by tangent. So when we do that in the numerator, that's what will happen. So let's go ahead and do it. And then we get a power rule over on the right one, right? The x cubed is going to be a nice power rule. So there's just a little bit of work to do. Oh, and the 2x squared is also a power rule. So I'm not going to write down all that stuff there, but hopefully that makes sense. So secant becomes secant tangent. That's kind of sloppy. Let me try to make that a little better. And then 2x squared is a power rule, so that just becomes 4x. Hopefully that's okay. Let me know if that's not. Second part stays the same. And then the first part stays the same. And then the power rule on x cubed is just 3x squared. We might as well square the bottom out. So when you raise a power to a power, you multiply the powers. Not necessary that you do that, but easy enough to do. What do you think? Can I clarify something? I haven't had any questions so far. I don't know if it's just things are okay or what.
Pretty confident with this.
All right, that feels good. Sounds good. It's easier than the limit definition, right? That's for sure. We don't have to do any limits. Although the quiz today is going to be some limits, but maybe after that we'll kind of stop doing limits for a little bit. A couple of head shakes. Believe me, there's actually a lot more complicated things that we don't do. So that whole epsilon delta thing, if you remember that, there's like there's varying degrees of theory, right? There's like the rules that we're doing right now, which is like no theory. It's like, here's just follow these rules. You take the theory a little bit further, it's the limit definition, which is tricky, but it's still just algebra. The epsilon delta thing that I just did that one day, that's like the ultimate level of theory, and we're not even touching that stuff. So anyway, just trying to say it can get more complicated. Is that okay? Can I answer some questions? Let me pose this question to you. In the next section, what we're going to start doing is taking derivatives like this and setting them equal to 0 and solving, because that's how we find maxes and mins and things like that. So if we had a fraction and we wanted to set that equal to 0 and solve it, how do you do that? Just kind of thinking back to solving fraction equations, or maybe the other question is, how do you make a fraction 0? Like, when is a fraction 0? Is the top 0? Is the bottom 0? Are they both 0? Not super important right now. Just wondering if anyone has a thought about that.
When either like y or x is 0. Right?
So the thing I'm trying to get at, I guess, is, and I'm not being super clear, is if you want a fraction to be 0, that means the top has to be 0. Right? The only way a fraction is 0 is when the numerator is 0. It has nothing to do with the bottom, in other words. And so just kind of looking forward, when we end up with these complicated fraction ones and we want them to be 0, we just ignore the bottom and we just set the top equal to 0. Anyway, we're going to talk more about that, but it just popped into my head as what's coming next, so I thought I'd just mention that. Okay, feel okay trying this one, next one? So give this next one a go. Again, I'm going to kind of slowly write some things down if you need some more pointers with it, but it's a really good idea just to give it a try when you're about to see the answer and all that kind of stuff, right? Just, it's a really important part of learning. So we want to identify the f and the g. I'm going to just start by doing that and kind of slowly write it down. Right? So the f, the numerator, g is the denominator. We're just going to use the quotient. I don't have a ton of room here, so maybe I will just write it down here. Just going to write the details. 2t squared. Oops. This is definitely one where you just don't multiply the bottom out.
I was just doing that and I was like, yeah, this is gonna take.
Yeah, exactly. Just that's not the point here. Especially like if we were gonna use this problem, like I just said, the denominator has nothing to do with solving equations, and it's just like, just leave it as it. Just leave it as that thing squared. Okay, so I had to shrink down my left-hand side, so it's kind of hard to read, but I'm trying to do f prime g minus fg prime, right? F is the top, g is the bottom, and it ends up looking like that. I think that looks fine. Just checking my work, seems okay. Thoughts about the quotient rule at all? On time here. I'm just going to introduce the chain rule. The chain rule is the one that usually people have the trickiest time with, which is why there's a whole page about it. No one here is writing, so I'm going to start going on to that. So again, the chain rule is what we do when there's something plugged into something else. Right, so maybe let me just do a couple examples of composition functions. So if we had like f is x squared and g was, I don't know, 3x plus 7 or something like that, if we plugged g into f, it would be that, right? That's the kind of thing we've been practicing. Like you take out the f and or the x in the f function, put in g. And so this is how we recognize something as being composition. Or something like, let's say we had, maybe let me color code this one. Let's say we had f was cosine of x, and maybe g was e to the 2x squared. If we did f of g, that's me writing down the f function and putting the g thing inside of it. And so these are the types of functions. And if you look, I'll flip back to the other page in a second, but if you look at that page, they're these kind of things. There's like, hey, we have an x squared, but there's something inside of it. Or hey, we have a cosine, but there's something else in there. And this rule tells us how to handle those things. Right? These are particularly tricky because you have two different things and they're not just next to each other or on top of each other, they're like inside of each other. So it's particularly tricky. Can I clarify something about just a couple examples I did there? Do people kind of see how that worked? Because the first step in these things is recognizing what's inside what. And so I'm trying to like give you some intuition there. So notice how, let me just remind myself. Yeah, we're going to really fill this page up. I should have given myself some more room on this next page, probably. We'll be okay. Okay, but notice what happens. When you recognize what's inside what, and then when you do the derivative, you do the derivative of the outside function with the inside one still there. That's what this piece says right here. And then you multiply it times the derivative of the inside piece. That's what this is telling us to do. So I'm going to rewrite that down at the top of the next page. So here's the chain rule. I'm just going to write the chain rule down right at the top here. If we want to differentiate a composition function, we do f prime of g of x times g prime of x. Just kind of, this is going to be good to reference. And so just look at the three there on the page, right? It's like the first one is an x cubed, and there's another polynomial inside it. Right? This one here is an e to the x with the 2x squared in it. This one is a natural log with a 1/2 t inside of it, right? So we're trying to identify what's inside what. I'm just going to do one example, and we'll pick up with this next week. I'm going to start with the one on the top left. So when I look at this h of y example, I'm trying to think about what are the two pieces? What's the f and what's the g? And so I'm thinking, well, it looks like something's being cubed, right? There's like a cube on the outside. That's what's giving me that intuition. And then I'm thinking, well, what's inside of it is a 2y cubed plus 16y.
So this is like the opposite of what we were doing all class. Now we're trying to go backwards.
In some sense, yeah. So previously you're talking about like this kind of thing, right? Like taking out the x and putting in the x plus h. So yeah, that was taking things out and plugging things in. Now we're looking at something where something's already been plugged in, and we're trying to think about what was plugged into what. So yeah, it's going in the opposite direction of that concept. All right, so, and the reason I arrived at that, because this one's on the outside, and this one's on the inside. Is that okay? Definitely gonna need more room here. I write much smaller, I think, when I'm not on my iPad, it turns out. At least here I can shrink things, I guess. Let me just shrink this a little bit. So is that okay identifying those two things? Because now we want to take their derivatives, right? This thing's telling us we need their derivatives. So I'm going to do their derivatives. And so G prime is an easy one. They're both easy, actually, because they're both power rules. All right, so F prime is just 3y squared. And G prime is 6y squared plus 16. And so we have one of the pieces we want. G of y is one of the things we want in the formula, and we now have that one. But we don't have the other piece, right? The other piece is not f prime of y, it's f prime with g plugged into it. So we still need to figure out this piece. And it uses this, but it's not that. We need to plug g in there. Yep. And then the g is going inside there, right? And so these are the two things we want to use. Right, those are the two pieces of the formula. Yeah, I wish I moved this a little bit. I'm gonna slide things around, and I apologize, but I wish I did this. But it didn't really work, did it? Let's see. So I just want to do that so I could write the answer down right below it. So the final answer then, H prime is going to be F prime of G of Y times G prime. And we have those two pieces, so it's going to be The reason it gets complicated, again, is because you have something inside the other thing, right? So it's kind of like you ignore what's inside it, take the derivative of the outside piece, but then put the other one back in, right? You like simplify it. In other words, doing this kind of thing, ignoring what's inside it and then taking the derivative of that is easier than trying to think about what the derivative of it is with it inside. So you kind of like ignore what's inside of it, take the derivative, but then remind yourself, oh yeah, but there was something in there. That's sort of like the F part of it. And then you need to account for the inside part somehow. And so accounting for the inside part is where the second part comes in, where you just multiply by the derivative of that inside piece. It's definitely the trickiest rule. And you can imagine how it eventually involves other rules, right? So it snowballs a little bit and it just keeps getting complicated. But we're just following the rules. We're trying to follow those rules. And if we can do that, we're going to be okay. Because I'm now on my iPad doing things differently than I'm used to, I've gone over top of this second example. And so I was going to insert a page here. And it might just be good in general. You may not have enough room on this particular page for your writing. You might want to have like a blank page to insert here, just so you can add enough notes for yourself to make this understandable later. So, this one right here, I'm going to go ahead and do on another page, but maybe we can finish some other ones on this page and then collect the ones that we missed and put them on another page. My goal here today, a little bit at least, is to do several examples of the chain rule, let you think about them yourself, one or two by yourself. And then there's just like not tons more, but there's an entire more page of additional examples that really start to combine all these rules. And honestly, the examples on this page 29, if you can do these examples, you kind of have a good understanding, I think, of all these rules. That's sort of where we're heading. So, we're really just starting to combine things is what I'm trying to say. So please, please, please just be active, be taking notes, be sort of thinking about this as we go. And if it's not clear, let me know. All right, I'm going to dive in. There's nothing else you guys want to chat about quick? Got a lot of people here. Great. Okay, so real quick, we're doing the chain rule, right? This is one right here. It's when we have composition functions. And so it involves one function inside of another function. And so it involves identifying those two things and then looking at their individual derivatives. And it kind of presents itself in a kind of confusing way. So let's just review the one we did on Friday. We recognize this example. I'm going to kind of just make a couple notes down here. We recognize this as something being cubed. And so that sort of made me think about, okay, well, there's something on the inside and it's being cubed. And so that's what made us realize that the outside function is x cubed and the inside function would be what the something is. And in this case, it's 2y cubed plus 16y, right? Just sort of, so thinking about the two separate things, what's inside what, and then you differentiate them separately. And we went through that whole process, right? So I'm going to kind of highlight what we did, but then sort of, I'm trying to re-explain it in maybe a shortcut kind of way, right? So we identified f and g, and then we took the derivative of f and then plugged g back in, right? That was sort of those two steps. It was like a one and then two step thing where we took the derivative and then plugged g in. And then g, which is the inside function, we also need that derivative as well. And so when we sort of wrote down the final answer, it was this f prime with g plugged in multiplied by g prime. That's what the answer kind of ended up being. Okay. But notice, and there's a bunch of steps to that, and I'm going to kind of keep thinking about those steps. But the intuition that we should be trying to develop right now is this. When we have something cubed and we take the derivative of that, we just sort of ignore the something and take the derivative of the outside piece, right? So like we just ignore what's on the inside, take the derivative of the outside, but then we multiply by the something prime, right? So you kind of ignore this inside piece. It's almost like the something just like doesn't exist in there, and you just take the derivative of 3x squared, or sorry, x cubed, and it becomes 3x squared.
But then you remember, oh yeah, there was something inside there. And so I also need to just have that in there and multiply by that derivative, right? So you're kind of ignoring what's in the inside and then accounting for it afterwards. That's sort of the general intuition we're thinking about. And I've just marked the heck out of this. So I'm going to erase basically everything I've written today, but just trying to help us think about how we're doing this. And I'm going to kind of reiterate that same thought process after every one of these examples. All right, can I clarify something about the chain rule before we jump into the next one? I'm going to look at the natural log one next, but I'm going to erase all this garbage that's on the screen right now. Anything? All right, so let me undo this stuff, go back to this space, just trying to think through that last example. And again, this example we will put on a new page in just a minute. But let's look at the next one. Let's look at the natural log one. So when I look at this natural log problem, it's a natural log with a 1/2 t inside of it, right? That's how we need to sort of start thinking about this one. So when I'm thinking about what's inside what, the outside function would be natural log, and what's inside of it, 1/2 t. Right, and that's a 1/2 t to the first power, and so it's like a nice easy power rule is what I'm trying to point out there. So you kind of identify the two parts, and then with the f part, it's like you're just ignoring what's on the inside, taking the derivative of just the outside part, so the f part, and then you plug the inside part back in. Right, that's how we're kind of thinking about this. Right, so with what we just wrote down in mind, you take the derivative of the outside piece, ignoring what's on the inside. Say natural log becomes 1/t. Let me just flash back to those derivative rules real quick. Right, the natural log rule, if that one's not in your brain yet, that's this one right here. Right, natural log just turns into 1 over the variable. And so that's what we just did. Right, f of t equals natural log. The derivative is 1/t. Right, so we kind of ignored the inside part, and then we say, oh yeah, but let's plug it back in because there was something on the inside. So then we say, oh yeah, but let me go ahead and plug the g part back in. And it's a compound fraction, right? You're doing 1 divided by 1/2. And so 1 divided by 1/2 becomes 2. Right, so that's the first component, right? That's the outside component. You kind of remove what's on the inside, take the derivative, ignore the inside part, and then you put the inside part back in. But then you need to account for the inside part because you kind of ignored it throughout that whole process, right? And so then you say, okay, but then I also need the derivative of that inside piece. So we take the derivative of the inside piece, which is just a power rule, right? 1/2 t to the first, nice easy power rule, just becomes 1/2, or 1/2 t to the 0, if you will, which is just 1/2, right? And so those are the two components of the derivative. And so we'll stick those back in there in just a second. Let me just pause and see if there are questions. And I'll do this cotangent one on a new page as well. So we'll kind of cross that one out here. I'll write the answer kind of right over top of that one. Questions about sort of the pulling it apart part, kind of looking at the two pieces separately. We'll combine them in the answer in just a second. Anything?
How did you get 2/t from 1/1/2 t?
Yeah, so if you have like 1/1/2, you flip this and multiply. This is how I usually think about it, at least. And so it becomes 1 times 2/1, which is just 2. Right, so this 2 is just doing this kind of thing. The other way to think about it is, right, if you have the number 1 and you divide it by 0.5, which is what you're doing, 1 divided by 1/2, it takes 2 of those to go into 1. Is it okay or other clarificational things like that? That's the kind of algebra stuff that's just good to just clarify. Just get it right out of the way. It's okay. All right, so then let's write down the answer. So then based on this work tells us we're going to take the derivative of w, and I'm just going to write down the chain rule again. It's f prime of g of t times g prime of t. And we now have both of those components. So it's 2 over t times 1/2. And the 2's cancel. And so it's really just 1 over t. And that's the derivative of this one. I'm going to say kind of a summarizing thing, try to get people back on track if you're kind of getting confused about where we were, especially it's been over the weekend, maybe that your brain's not where it needs to be. I'm going to say something, but are there questions about the specific example that I can clarify first? So if you've been kind of, if you haven't been closely following along or whatever, and you're wondering like, how do we get from something easy like the power rule to these kind of really complicated examples really quick? I just want to remind you of the progression. We've got all these rules, right? We've got all these rules in this list, and a lot of them are pretty straightforward, like the power rule. Like the power rule is not so bad, right? The constant function rule makes sense. Sine turns into cosine. That's not bad. We take all these simple rules and we apply them to more complicated situations where it's not just one separate thing, right? So the complicated situations are the ones at the bottom here that are in red. It's when we have simple things, but they're being multiplied, or we have simpler things, but they're being divided, or what we're working on now is sort of simpler things, but they're being plugged into each other. And so rather than having, infinitely many rules like, oh, what do you do if there's 1/2 t plugged into a natural log? Or what do you do if there's something inside an x cubed? Rather than having like infinitely many rules, we're trying to generalize these situations into breaking them down into their smaller, simpler components, which are listed previously, right? So like 1 through 13, for the most part, are the simple ones, and then they get combined in these more complicated ones. But it really just boils down to the simpler rules is what we're trying to do. I know it looks complicated, but we're taking something that's complicated and reducing it to simpler rules is one way to think about it. Okay, so I just wanted to sort of get us back on track there if that wasn't clear. Can I clarify anything about these notes maybe now that you finished writing it down? The one we just did. Anything? Okay. All right, so get a couple more, and then I'm going to ask you to maybe think about one or two. Yeah, let me do this last one, and then I'll let you think about the two that got crossed out. Right, so the f of t function here is clearly a sine function, right? And we have a rule for sine, but we don't have a rule for sine with some polynomial plugged into it. But we recognize it as that, right? It's a sine function with something else inside it that's a polynomial. And so that's how we think, okay, well then the f function, the outside function is the sine, and what's inside of it, I'm sorry, I didn't mean to write f prime, just f, is sine, and the inside function would be the polynomial part. And again, so we don't have the rule for this specific example, but we do have a rule for sine, and we do have a rule for polynomials. And so we sort of break them apart, do those things that required by the rules, and put it all together. And this one's not too bad, right? Because sine just becomes cosine. Yeah, I'll just spread this page out. So the derivative of sine is just cosine, no big deal. And then g is a power rule, and so that's not a big deal either. right? And then the G prime part, this is part of the answer. That's going to be the thing we multiply by. We need to take the F part, the outside part, a step further. And plug the G part back in. So it's really cosine with the 2t squared plus 1, plus t, excuse me. And then we just put it together. Right? It's going to be the thing on the top multiplied by the thing on the bottom. So that's fine. Let's finish it. So based on this work, the derivative is going to be cosine of 2t squared plus t times 4t plus 1. All right, this is my f prime of g of t times g prime of t. I would love to answer a question. I just really think this is a good time to clarify something. I just don't know if people are just checked out a little bit, maybe just trying to get back into it. Maybe I know that feeling where it's like, I'm so lost, I can't even ask a question, but it'd be really good to try to muster something if you're confused. All right, well, if not, I'm gonna slip another page in here, like I mentioned, and we'll do these two that got X'd out. I think I can slip a page in here now that I've paid for this thing, yeah. So let's just go right in there. Yep, blank page, great. So I'm just gonna copy those two back over. So it was, so from the last page, e to the 2x squared was one of them. And let's just put a line right here and we'll do the other one right next to it. The other one was cotangent of y squared. And so hopefully you can kind of see these ones aren't super complicated because it's like e to the x with something in there, right? It's kind of like the cotangent especially, right? We have a rule for cotangent and there's obviously a y squared inside there. Although I don't know if we've actually done the cotangent rule yet together. And so this is one you'll just have to look here, right? So here's the cotangent rule. When you've got cotangent, it turns into minus cosecant squared. So you have to think about that one. I think here. All right. I'm going to let you think about these yourself for just a minute, and then maybe we can split up and do some of the examples in breakout rooms is what I was sort of thinking about. No questions before we look at that? All right, so let me put these back up. Start pulling them apart and thinking about the two pieces. I was going to summarize the last one. Sorry, I wanted to just say one real quick thing about this one. In case you're still confused or you're thinking about how to simplify this, right? We don't have a rule for sine with something in it. So we instead realize it's sine. We know how to take the derivative of sine. So we kind of ignore what's inside it, right? That second part is totally ignoring the inside part. And we just take the derivative of the outside part. And then we say, okay, but we're going to stick the inside part back in. Right? So you ignore what's inside there, take the derivative, and then stick it back in. And then to account for the fact that you ignored what was inside there, it's one way to think about it at least, you look at the inside part, and then you take that derivative, right? And then you just put the two things together in your final answer. Right? That's sort of the simplified way. So you don't have to write down all this work and think about the formula and stuff. You're just ignoring what's inside there, taking the derivative, putting it back in, and then accounting for what's inside later. Okay, that's my sort of quick and dirty summary of the shortcut. Okay. Anyway, so you can kind of think about the same thing, right? It's an e to the x, but there's something in there. There's a cotangent, but there's something in there. All right, so I'm going to kind of write down the details, but see how far you can get by yourself, and then we can check the answers together. So when I look at this one, the outside function's e to the x, inside function looks like 2x squared. On this one, the outside function is cotangent. The inside function is y squared. Right? So ignore what's on the inside and then account for it later. All right, I'm just going to stop there for a second, let you just think about how to finish that one off, and then we'll look at it together. I was trying to think if there'd be a good way in these situations if someone's like totally lost and they wanted to just talk to me one-on-one. Like usually when I ask people to do this, there's usually a couple of people who just don't even know how to start, which is fine. But usually in those cases, I'm able to they raise their hands. I'm able to come over and give them some one-on-one attention. I think if someone wanted to ask a question, I think we could just like shoot ourselves over to a breakout room, basically, if I'm not mistaken, while other people are doing that. I think I'm working on that right now. So anyway, let me know if you want to chat. Maybe we could pop over to a breakout room. Yeah, we totally could. So let me know. All right, I was just over in a breakout room with someone asking a question, so that was good. Yeah, that could definitely work in these situations. I'd like to start doing this a little more, giving you some time to think about this stuff. And popping over to a breakout room could be a good way to get some quick one-on-one help here. Let me see. Okay. Anyway, so let's look at this one. So hopefully you had some time to think about it. We break them apart into the two components, right? You take the derivative of f, just stays the same, right? That's the best rule out there. E to the x just stays e to the x, but you want to have g back in there. So f prime with g in there, it's going to be this, right? So that didn't change actually. So you're kind of having the same component, which is what happens when you have an exponential function. When you do e to the x and you take the derivative, it stays the same. But then you account for the inside piece with the g part, right? And so g prime is just a power rule for x. And so you have the two components right there, just multiply them together. Let's call this, what was it called in the paper? Is it called P or something? Oops. So P prime then is e to the 2x squared times 4x. We've got our f prime of g of x, got our g prime. Is that all right? Questions about that one at all? You guys get that? All right, we do the same thing with the other one or a similar thing. So I just need to remind myself of the cotangent rule, right? Cotangent becomes minus cosecant squared. So I'll have to drop down below. We have f prime times minus cosecant squared of y, but then we put the g back in. All right, so you ignore what's in the inside, take the derivative, but then put the inside back in. And then g prime again, that's a nice, easy power rule. No problem on that one. Those are the two components. Just multiply them together for the answer, right? What is this was called h in the problems. This was h. So h prime then is this piece times 2y. Answer questions about everyone? Yeah, go ahead. Sorry.
For f prime of g, I did what you did, but was there a reason why the 2x squared went back into the exponent instead of just being in parentheses, like what you did for the negative CSC? Like, does it only go back in for exponential functions? It go back to the top instead of just being in parentheses next to it?
So it was in the exponent to start in the problem. I don't know if you see this, but this is e raised to the power of 2x squared.
Mm-hmm.
That's different than, so I guess I'm a little confused. That's different than cotangent. You can't just have cotangent by itself. Like you can't just have cotangent without anything in it. You need to have something plugged into it. So it's not like multiplied. It's not cotangent times y squared. It's cotangent at the point y squared. Or you could have e times a number like 2, because e is a number. E is like the number 2.7. So e, you can raise it to powers, you can multiply it by things, you can divide it. But cotangent, natural log, all the trig functions and things like that, you need to have things plugged into them. So natural log is another one of those things, right? ln by itself is meaningless. It needs to be ln at some input value. Right, like ln, for example, looks like this. And so t would be the x-axis. And so you're saying at some t value, right? These are t vals. What's the output of ln? Does that clarify? Is that sort of the thing you were talking about? I don't know if that's
Yeah, calm.
so maybe back to this example real quick. This was an exponent, right? It had e to the 2x squared. We took the exponent out just to think about the outside part. We took the derivative of the outside part, which just stays the same, right? That's a nice one. And then you just put the inside part back in, though. And so that's where, it doesn't get multiplied by that because we took it out of the exponent and then we put it back into the exponent. Other thoughts about either one of these? All right, so that's the chain rule. All right, we did 5 examples of that one because it's a tricky one, and that's why it has its own homework set with a bunch of problems, because it just manifests itself in so many different ways, and we just need to be able to recognize it in the moment. So that just takes practice, right? That's all. That's why this is just one of those topics where it's like practice makes perfect kind of thing. Whereas, sometimes if there's a formula or something, you just need to plug things into the formula a couple times and you get it. But this is like, there's so many different versions of the same thing in this. For example, let's slide back up to the last page. There's just a whole bunch more examples in the rest of the section, and I don't want to get too burnt out today, so I'm going to spend a little time on a couple of them. Probably let you do a few in breakout groups, and then we'll just do the same thing on Wednesday, and we can start digging into the homework on Wednesday too. So bring some homework questions that we can work on together as well. But this is the sort of the more examples section, right? And so this is more example number 1, but there's a whole bunch more on the following page too, right? These are all just more examples, and they all combine other rules. And so we're starting to combine rules, and we just keep taking it up a notch. All right, so let's start with this first one. I'm going to do this first one, then we're going to do some breakout groups with the other ones. So when I look at this first one, it's kind of complicated because if we want to do the derivative, we have 2 things being multiplied in the first thing, right? We have sine of 2y times e to the y. So when we do that derivative, we're going to need the product rule. And then when we take the derivative of the cosine part, it's a cosine, but there's something inside of it, and so that looks like a chain rule. All right, so we've got 2 of the things we've just been learning here. And I'm recognizing it as a chain rule and a product rule. And then also notice, I'll write this down in a second, but then when we start digging into the product rule with the sine of 2y in there is going to be a chain rule itself. And so we have a product rule and a chain rule, and the product rule has a chain rule in it. Right? They start to snowball. And the reason this is real stuff, because when you have real world examples of you're actually in a science, out in the field and you're making a function or you find something from the literature, they're not like nice functions. They're kind of nasty looking functions, and we need to apply the rules sometimes. All right, so I'm going to set this one up kind of slowly before I let you guys think about your own here. So when we start doing this, we're going to think about the derivative. How much room do I have there? I'm going to try to write it all down and cram it in right here. So we're going to do the derivative. I'm going to do the product rule. Should I color code this a little bit? I'm going to color code it. I'm going to change the product rule to a different color. Let's change it to blue. I'm going to try to color code this a little bit so when you look back at it, it kind of makes some sense. So the product rule is going to be in blue. So I'm going to write down the product rule. Right? The product rule says f prime g plus f g prime. All right? This is the product rule. I'm going to erase that arrow in a second, but you can see it's in blue at least, hopefully, so it corresponds to the product rule, right? And I'm doing f prime g plus f g prime. I don't want to keep flipping back between the tabs. Hopefully you can have that tab out. Look at the product rule and see if that's what it looks like. I can at least label it, I guess, right? So this is my f prime g plus f g prime. And then when we do the chain rule for the second piece, it's going to be in purple. Right? So the second piece is going to be the derivative of the cosine part. And we'll need to do the chain rule on this one. Might as well just label this. Everything else is labeled. Is it okay? And I guess the thing I'm trying to point out here, the thing that makes this just another level of complexity, not only is it the product rule and the chain rule, but then when we do the d over dy of sine of 2y, that's going to be a chain rule itself. Right? Because we have a sine with something inside of it. And so as long as we're kind of careful about this, and I don't need to see all this work on a test, but this is the kind of stuff you want to write down so that when you go to the homework later, you remember the kind of things we talked about. So I'm going to look at some of the individual components real quick, but questions about how we're kind of dissecting that and thinking through what we're going to do? Oh, and let's just do the exponential rule too, right? And then when we do d over dy of e to the y, that's just an easy one. It's just the exponential rule, it just stays the same. So we don't have to think too hard about that one. It's okay so far? I'm just going to write down the individual things on the left here probably, and then we'll put it together. Right, so when I take the derivative of sine of 2y and I recognize it as a chain rule, I recognize the outside function as being sine and the inside function as being 2y. Right, and so then f prime with g plugged in is going to be minus cosine of 2y. And g prime is just a power rule, which is 2. And so you combine those things to get the answer. And I know we're going kind of quick here. It's like, oh, we just used the train rule, and now we're just cramming it inside of this more complicated thing here. So I'm not expecting everyone to fully be on board here, but we need to start ramping up the complexity.
Why is it negative cosine 2y?
Because I messed up my rule. Sine becomes cosine. I always have a hard time remembering which is which. So sine becomes cosine, cosine becomes minus sine. Thank you. So it's just a positive there. So I just deleted the negative signs, guys. So there should be a plus right there. Plus right here. Yeah, so sine becomes cosine. Cosine becomes negative sine. I always mix those two up. So that's going to be that's going to go into the sine of 2y spot, right? That's just like one of the components that's going to go inside there. Happy to sort of go a little slow here and see if there's some questions about that. All right, let's just do the exponential rule real quick. I mean, not the exponential. Let's do the chain rule on the cosine part. So when you do the derivative of the cosine of 4y squared, we do a very similar thing, right? The outside function is cosine. The inside function is 4y squared. And this is where the negative sign comes from. When we do the derivative here, we get minus sine. And let me go ahead and just do the whole thing. F prime with g plugged in, you get minus sine of 4y squared. And the g, just a power rule. And so putting it together, that derivative is just those two things multiplied. So that's going to go into this part, right? And we have it all, right? We've got the components. E to the y just stays the same. And so we just kind of put the things in that are missing. Right, so final answer, p prime of y is going to be, we're just continuing. Let me go ahead and draw this line right here. We're just kind of bringing down what we had, and now we have all the different components. And maybe I can just slide this over into this nook a little more. So I'm just going to write in the individual components. So it's going to be cosine 2y times 2 times e to the y, sine 2y e to the y, sine 4y squared times 8y. All right, I'm going to stop there. And I think I've changed my mind about what I'd like to do. I think I'm going to leave the group work and stuff till next time. So we've got an entire more page, an entire another page. I'm not going to scroll right now, but if you scroll to the next page, you'll see there's 4 more examples that are similar, that are kind of like combining product rule, quotient rule, chain rule together. And so we can spend some time next time doing that. What I'd like to do now is just turn it over to questions. If there's specific questions about homework problems or things on this page that people want to carefully go through, we can do that now. Or if some people, if you're really anxious to get out of here or whatever, I don't want to keep you over time this week. So you guys can let me know what you want to do. Are there, like I know Gregor started working on the homework. Have people looked at any of the product or quotient rule homeworks and are running into some issues at all? Or do people want to go there right now that we have a little more work under our belt with the stuff, and sort of see if they make sense or not? Just going to pause for a minute and see if anyone can come up with a question or not.
Can you just explain how you set up the product rule for the sine 2y times e to the y?
Yeah, so I was recognizing this as being two things multiplied, and I kind of threw a little multiplication sign in there right in the middle, right? I'm recognizing it as sine of something times product rule real quick. I'm sort of thinking about this product rule with this one being like the sine part, and this part being e to the y. And then I'm just trying to apply the rule to that. And so keep this in mind. Again, if you don't have this out in front of you, I've said it a million times, you really just need to get it out in front of you so you can reference it as we're doing this. I can't keep flipping back and forth, distracting the people. So you just need to have it out in front of you. And so part of the reason is you don't have that out in front of you and you're wondering why, and I don't mean anyone in particular, but like if you're having a hard time recognizing the product rule as being the product rule, it's because maybe you need that reference out so you can take a look at it. So with this in mind, and again, hopefully you have the product rule out, this kind of thing out in front of you, right? It's f prime g plus fg prime. And so when I flip back over here to this and I recognize this as being the product rule, I flip back over, and that's exactly what's going on. And I labeled the f prime and the g. Right, I'm trying to take the derivative of the first piece, leave the second piece alone. Leave the first piece alone, take the derivative of the second piece, right? That's what the product rule says. And again, I don't want to, well, maybe I'll flip one more time, but this is exactly what it says right there, kind of mapping it out on this problem. And then we start to go inside there and think about, okay, well, what are those individual derivatives? What's the f prime? What's the g prime? And start to think about what rules apply to each one of those cases. All right, so then, like I said, I'd like to do like just a few breakout rooms and just let you think about these and potentially think about them together. And maybe we can just sort of start by making note of what we're going to do on each one. Does anyone have an idea of like what rules are going to be involved in this first one? We've got two things being multiplied. Yeah, go ahead, John.
So it's a product rule, but inside of the product rule is a chain rule.
Good. So it's going to be a product rule because we've got things being multiplied, and it's going to have a chain rule inside because we have the e to the 4x squared. And so that's the kind of just recognizing that right off the bat is sort of like, all right, I sort of know where we're heading, and then you start to dissect it and be a little more careful about it. That's perfect, though, yes. The second one then, so we've got natural log, so it's an ln rule, right? But then what's going to happen when we take the derivative of the inside part?
Quotient.
It's going to be a quotient rule, good. Right, because you've got the derivative or the inside part, the 2t over square root is a quotient rule. Or you could also rewrite that as potentially, you could make it simpler to make it into a power rule. I'll just sort of mention that. I'm gonna do it as a quotient rule just to make it harder. No, make it just give you something else to look at. But you could transform this inside part into a power rule. Maybe think about that. What about this one? We've got square root. This is kind of similar to the one that Rashid was asking about with the square root of ln, or what was in there? Square root of tangent, was it? But now we've got a square root with a product inside of it, right? So what are we doing on this one? What's the first rule?
So it's a product rule inside of the chain rule.
Yes, good. So it's a chain rule first, I would say, with a product inside. And when I say like chain rule with the product inside, just kind of jumping to the derivatives, right? If we have a chain rule, like the thing on the right here, this is the part that's going to end up being the product rule, right? Because you take the derivative of the inside, and the inside is going to end up being a product. That's sort of what we're talking about here. And this is the same thing on the next one too, right? It's also a chain rule with the product, but it's just a different type of chain rule. I think I can do that. How do you paste it though? You can copy it, and then what? It's not paste.
Hold it. Is that the iPad? Hold the cursor down.
Nice. Thank you. What else? What other options are you getting there? But what I was noticing was people are not doing the notation and writing things out sort of the way I have been in class, which I'm not going to force you to do necessarily. But I think what you're finding is when you don't write out the details, it's easy to get lost in a complicated problem like this. And so I would really encourage you to write out the kind of things I'm about to write out. So like, we're going to do the product rule, right? So what does the product rule says? It says, take the derivative of the first piece, multiply it by the second piece. Add to that, leaving the first piece alone, take the derivative of the second piece. And I've done, I write it out like this every single time, partially so that it makes sense when you look at it later, but also partially so that we have a roadmap to see what we're going to do as we move forward. Because as we keep going here, we need to, it just gets complicated, right? So we've got f prime g, we've got our fg prime. I'm going to do a simple power rule on this one. But the e to the x one's a chain rule. And so then we've got a chain rule inside this. We're going to need some more notation for that, and then we'll put it all together. Right. So, but noting, doing this, and it doesn't have to be this detailed, but having a roadmap of what you're about to do prevents you from making mistakes, which is particularly important in math when things, one mistake is the difference between getting a web work question right or banging your head against the wall for an hour on a web work question. Just being careful, right? So anyway, let's do the chain rule part. So if we're looking at the chain rule on that one, that's a chain rule with the outside function being e to the x and the inside function being 4x squared, right? And so you want the derivative of f with g plugged in. Let me move this over a little bit. All right, so remember the way you think about that, the way I'm kind of trying to get us to think about this is you just do the derivative of f. So e to the x just stays the same. And then what are you doing with it? You're putting the g back in. So we have the 4x squared goes back in. Right? See if I can change those inside pieces. So that's the one component. And then since you kind of ignored the g part, that's where you'd take the derivative of g with the power rule to get 8x to the 1. And so this is that chain rule part, right? This is going to be, just to kind of summarize it, when we think about taking the derivative of e to the 4x squared, we get 8x, or let me write it the other way. We get f prime of g of x times g prime. Right? So that's going to be the component inside the chain rule. Is that all right?
Why are the exponents the inside?
The 4x squared, you mean?
Yeah.
So as I was kind of just honing in on this one particular problem, I'm trying to think about the rules we have and what I know about those rules, right? So when I'm looking, just kind of thinking about all these rules, I know that we have this one. I know how to take the derivative of e to the x. It just stays the same. And so I'm recognizing it as having something to do with that, right? And so I'm using that just by thinking about this as being e to the x with something plugged into it, right? So I'm trying to break down e to the 4x squared because we don't have a rule that says, what do you do when you have e raised to the power of a polynomial? And so I'm trying to break it down into two separate rules that we have. And I'm recognizing it as the e rule, which we know, and the power rule, which we know. And I can see, so maybe that's not the question. Is the question that how do we know that the 4x squared is inside the e to the x? Is that maybe the question? Or,
Well, basically, why is it the G, basically?
I mean, I guess can I clarify? Were you thinking maybe it was the other way around? Maybe g was e to the x and f was 4x squared?
Yeah.
Okay, so let's think about that. If we had f being e to the x and g being 4x squared, and we did f of g, right? That would be taking, I just wrote the same thing down. Sorry, I meant to switch those. F was 4x squared and g was e to the x. Then that would be taking the x out of f and putting in the g. Do you see that? Let me color code it real quick here.
I guess.
What if we made let's make it blue or whatever. Right, so when I'm looking at the outside function, in this case f, if I was going to plug something into that, you remove the x part. And so this over here, without the e, right, this is the function f without the x in it. And then if I was going to put something into that x, like e to the x, it would look like this. Right? Just taking this piece and putting it inside there. And I mean, what I'm trying to do here is contrast what it would look like to have these two switched. And I think understanding how they look differently is, if you can see that, that's what we're getting. That's what we're going for. I'm going to write down the final answer here. We've got all our components. I'm going to erase this stuff. And so our final answer then, let's do it in blue. F prime of x using the product rule is what we just wrote down on the right, just kind of all with the things in there, right? So the power rule on x to the 9th is 9x to the 8th, e to the 4x squared. And then we're going to do plus x to the 9th, and then the derivative we just found. Right, this thing is going right in here. Times e to the 4x squared times 8x. That's the final answer. You can simplify it more. There's things you can do to simplify that I'm not concerned about the simplification. If you really wanted to, you can. What can I clarify about that? We're just going to look at the second one in a second, and then we'll move on to the other two on Friday. Anything? All right, let's check out that natural log one. So it's another chain rule, or I guess it's a chain rule. The first one was a product rule. We're going to do the chain rule because we have this fraction inside of a natural log. And so our outside function is the natural log, and what's inside of it is the 2t over square root of t. And I'll just remind you that square root is the same thing as t to the 1/2. And we're going to want to think about it as t to the 1/2 because when we take the derivative, it's an easy power rule, right? And so this one's just, it's really just a chain rule, but then we're going to have a quotient rule inside it. So it's a little bit different than the last one, right? The last one was a product rule that had a chain rule in it. This one is a chain rule that has a quotient rule. So let's keep going. So we take the derivative of f. I know that the derivative of natural logs are just 1 over t. But I don't want f. I don't want just f of t, in other words. I want f prime with g plugged in. So let me do it this way again. Here I am taking out the t. Right, what I've written down on the rightmost part of this page that I'm going to circle real quick in an ugly kind of way is the derivative of f without the t in it, right? So it's just 1 over blank space. The chain rule tells us that to do the chain rule, we want the derivative of the outside piece with the inside part plugged in. And so I'm just trying to write that down, right? And so you can see I've got that here. I just need to put something into the spot with the blanks are. And what goes in there is the function g, right? So I want g of t in there. G of t is this square root fraction thing. So it's 2t over square root of t. How's that simplify? If you have 1 over a fraction, what do you do there? Talk about that a couple times. You just flip it up. Yeah, right. Yeah, exactly. You flip it. You multiply, flip by the reciprocal. Multiply by the reciprocal. And so this is one of the pieces that we're going to use, right? This is the f prime of g. Now, g prime is where the quotient rule comes in. So when we do g prime on the bottom, we're going to do the quotient rule because it's a quotient. And it's a bunch of power rules. And so we just did we do the quotient rule? Or I guess I was doing it in someone's room. Anyway, it's a bunch of power rules, right? So the quotient rule would be f prime g minus f g prime. Take down the power, subtract 1 off the power. All over g squared. Right, so the quotient rule is a bunch of power rules, and then that can simplify down to something nice. Again, I'm not necessarily needing it, but in this case, it actually turns into something that's not too bad. So this becomes, in the interest of time, since we're almost out of time, this becomes t to the 1/2 over t to the 1. You subtract those powers, we'd have t to the minus 1/2. Got this fly flying around here, driving me crazy. And so that's the other piece of it. And so we can write down our final answer, right down the bottom here. P prime of t is f prime with g plugged in times g prime. And that can also be simplified. We can talk about simplifying it if you guys are interested. I guess I'll just write down the final answer. If you want to simplify it, it turns into 1 over 2t. Because you kind of have like the square roots cancel. But I'm fine with what I boxed in. Again, the point of these is, do you understand the derivative rules? Can you kind of put together complicated ones? I'm less concerned about algebra skills. So that's the end of the period. Oh, I see something in the chat. Do you have to simplify f prime of g at the beginning? You can. Yeah, so that this original thing can also be simplified, Gregor's pointing out. You're welcome to. I'm not super concerned, right? So that could simplify. You've got t to the 1/2 over t to the 1. And so that could be 1/2 t to the minus 1/2 if you wanted to.
1 over 2t over the square root of t. I made the mistake of leaving the 1 over it. So do you have to simplify it so that it's the square root of t over 2t?
Oh, you mean you kept it like this?
Yeah.
You do want to simplify that because that's a compound fraction, and we don't want to have compound fractions. Yeah.
So we're going to do a little quiz on derivatives at the end of class here, and it's going to be a basic quiz. I'm not going to get into the weeds on some of these more complicated ones, like the ones that we're in the middle of right here. I think I'll throw in a quiz maybe next week once we've had a little more time to digest. So the ones this week will be a little more tame than those. But we were on the middle of this page and we had these 2 left here. And so I was going to start with that, but I'll just remind you that I extended the homework for Wednesday. So the homework for Wednesday is now due tonight. And I'm just generally flexible about those homework. So one more questions before we get started? Anything you want to talk about before we just dive into these here notes? Okay, so the thing with the ones on this page are we're combining chain rule with other more complicated things, right? And so the one on this, the next one on the page here, we want to think about this as being, let me get my pen going. This is being what's inside the square root And we always think about square roots as the 1/2 power, right? And we do it that way because we can do a power rule when we have it like that. And that's something that actually is going to be on the quiz today. So taking a square root and taking the derivative means a power rule, thinking about it in terms of a power, right? An exponential. And then we use the chain rule with the inside piece being the exponential times the polynomial. And I'm sorry, that was the inside piece. That's what I meant to say. That's going to be the g function. And the outside piece, like what is that inside? It's inside a square root. And so it'd be like square root of x, x to the 1/2. Let me see if I can I get this, put that hat there last time, and now I think I can't move it. There we go. And this one ends up being tricky because then we have to use a product rule on the g function. All right, so this one ends up being a product rule. And it'll have an exponential with a power, and so it's also going to have a chain rule inside of it. And so the inside piece ends up being the tricky part on this one. And so let's just do the derivative of the outside piece first, right? So the derivative of f prime. Again, this is the kind of thing I like putting on quizzes. Just like that. And we've seen that a couple times. Let me know if that makes sense or not, but you bring down the power, subtract 1 off the power, right? No big deal. And so remember, in doing that, we're ignoring what's on the inside. The inside piece, we're just totally ignoring. And then we go ahead and we put it back in. And so let's put it back in. Oops. So it's going to be the thing we just wrote down. All right, so I'm just rewriting the f function, but I've left a bunch of room in there because instead of having just x in there, we're going to put the entire g function in, right? So it'll be this, this 8, e to the 2x times 8x cubed. Right, so that's the first component. That's sort of the tricky part of the chain rule, is usually thinking about the outside piece, right? We kind of ignore what's on the inside, take the derivative, and then put the inside back in. Is that okay? One of the tricky things on this one is then the g function usually isn't as bad as this one, but this one ends up being a product rule, and so we do have to think a little bit more carefully about g prime then. That's okay? So then g prime ends up being, oops, not f prime, g prime. How much detail do we want to do here? I will just erase this here. Yeah, I'll probably end up going down into that bottom one, and then we can just add another page. Excuse me. So let me just do the detail there. So g prime then is f prime g plus f g prime. And yes, I'm writing the details out, and my hope is that you're doing that too, so that when you look at it later, it makes sense. Even if it makes sense now, we want it to make sense when we're studying for the test. We want it to make sense when we're studying for the final. We want to have these notes. And so, and you know, this is important because if you don't write this down, you might miss this part, right? This ends up being a chain rule. And this one's just an easy power rule. Thank goodness for power rules and exponential rules, so we don't have to do too much, but sometimes we got to do some chain rules. Let's see. We want to see the details on that chain rule. Might as well just write it down, right? So let's do the chain rule. This is a chain rule with the outside function being e and the inside function being 2x. Right, and so then we take the derivative of the outside function, and then we plug g in. That just stayed the same, really, right? And then we account for it with the g prime. And so we put both those things together for this derivative, right? So the derivative of e to the 2x, I'm sorry, I messed up the derivative of g. This should just be 2. It's just 2e to the 2x. All right, it's getting kind of weedy. It's getting like really, feel like we're getting into the weeds here. It's getting real busy on this page. Let me just pause here, make sure everyone's gotten everything written down, and then we can kind of summarize it all. Should we write down the power rule real quick there too? So the power rule right here is just 24x squared, right? Okay. I think we have all the pieces. So we can put it together in a final answer here in just a second. Can I just pause and see if there are questions? Yeah. So notice how the question for those who are online, the question was in this chain rule part, why isn't it the other way around? Why isn't it f equals 2x and g equals e to the x? And we talked about, this is something that's come up a couple times now. Notice how e to the 2x is in the exponent, right? So you're taking the 2x and you're putting it up into the exponent of e. And so that's implying it's being plugged into something else, right? In other words, if you did it this way, if we did f of g in this case, it would be that. Do you see that? See how that's different than switching it around? So the fact that it's in the exponent is sort of what's telling us that the outside function is the E1. Yeah, that one's a little bit tricky because it's an exponent thing rather than, if it's like sine inside of there's something inside of sine, like I feel like ones like this are pretty obvious, right? It's very clear what's on the outside, what's on the inside. This has come up a bunch of times. So if you see an exponential one with something in the power, the exponential is on the outside. Okay. All right, let me get rid of some of that stuff. Okay, other thoughts before we put it all together? We've got all the pieces. All right, I've got the G prime. It's a product rule with a chain rule in there, but we have the pieces, and then the F prime of G is at the top there. So let's just go ahead and write down the final answer. So, and I'm just going to move this one down to the next page, just so I can have room here. So you might need another page here. So the final answer that we have of M prime is going to be F prime of G of X. So that first thing we worked on up top there. And I should have just realized how big this is going to be. We're going to need lots of room on this one. I'm going to slide this one over. F prime of G of X times G prime, which is the product rule. So it's going to be 2e to the 2x times 8x cubed plus e to the 2x times 24x squared. That is a big, big problem. I wouldn't expect I'm not going to like hammer you on one of those on a test or something, but there are a couple in the homework that will challenge you a little bit. That might be. Let me just sort of try to figure out how this. So this piece here is the F prime of G of X. And this piece here is the G prime. And this one was particularly nasty because the G prime was a product rule. All right. Thoughts about that one? Questions? Let me see if the chat's going. Nothing in the chat. Okay. That might be the worst one or the sort of the hardest one on this page, just kind of looking at all the different parts there. So, I wouldn't feel bad if that doesn't make it's not crystal clear, but if there's something I can clarify, this is a good time to, like, I just feel like if you get this one, you're in really great shape. Love to get some people there who are kind of close, but maybe something's confusing. Just wait a second here. Anything? All right. I'm going to throw another page in here, and let's just do the last one a little bit quicker. The last one's not as bad, so I'm going to just rewrite this one down on the next page. And so hopefully you can recognize this again as a chain rule because something's being squared, and we'll have another product rule on the inside, but it won't be nearly as bad because it won't be a product rule of a chain rule, right? So just kind of, we can do this one a little quicker. So this is a chain rule with the outside function being x squared and the inside function being, I'm sorry, we have y's in here. I should have done y squared. Y squared, and the outside function being, the inside function, excuse me, cosine times e. And so, yeah, we're going to need another product rule, but this is a kind of an easy product rule. And this is the kind of product rule that I start off with on quizzes today, for example, low level, simple kind of product rules that are just, do you understand the basic rules? So anyway, let's do the f function first. So the derivative, just 2y, no big deal. And then we stick the g function back in. So it's 2 times cosine y e to the y. I feel like that's initially this f part, this kind of thing is initially the thing that's confusing people. But I've been talking to people a lot, sort of in office hours and stuff, and I feel like people are starting to get that. Okay. Is that all right there? Okay, and so then we just do a product, or yeah, product rule on this one. And I'm just going to write the answer. This is the kind of thing we eventually just want to be able to do, is like, okay, I know the sort of general formula. If you don't remember it, it's this right here. Right? I have that committed to memory, and I know I've written all over this now, but I know what that is, and if you don't know what it is, it's out in front of you. I'm just going to do f prime g plus fg prime, right? So f prime, so cosine prime is minus sine. So that's f prime g plus f g prime, right? E just stays the same. So I just sort of did the product rule without the details. Hopefully that's okay. And then you just multiply those two things, right? You multiply the two things we just calculated, the f prime of d of x and the g prime. Just put them right together, and that's the answer. Right, so then p prime is those two things multiplied. And I'll just remind you, I'm not super picky about simplifying. You know, we'll worry about simplifying things in the next section when we actually want to start doing things with derivatives. Right now we're calculating derivatives. Next section we do things with derivatives. That's really when we want to be able to manipulate and simplify things. Right now, let's just focus on the rules. All right, anything about these rules? What do you think? I think, and because I think the next thing that we're going to look at is starting to use it, if I'm not mistaken. We talk about higher order derivatives real quick. That's right. And then we'll talk about how to use it. Yeah. As in, you're talking about this two right here? Okay, yeah, so the question was, you know, when you go from here to here, it's a little bit confusing because we're doing the kind of pluggy E thing, and that wasn't what I really meant to say. We're plugging things into each other, which is confusing, right? So let's look at that really quick. So if f of y is 2y, right? When we plug something into f, you just delete the y. So there I am deleting the y, but I'm going to just leave a space for it. And then when we plug something in, we just put it into that space, right? So if we plug in g, for example, it just goes into the space. And so you should think about there being a parenthesis there, basically, right? When you remove something, it like makes a parenthesis, because then if you stick something in that's really big, it needs to be inside that parenthesis. And so that's the way we kind of think of this. Okay, yeah, it's 2, and then there's a parenthesis. And what is g of y? Oh yeah, it's this nasty thing. But yeah, it should be when you take out the variable, think about putting a parenthesis in. I've done that most times, right? And I'm really encouraging you to try that when you're doing these problems. Other thoughts about that at all? How are we doing here? Okay. Let me just erase this part. And let's just talk real quick about higher order derivatives. And I think we did most of this next page, but then we can also finish off with this one maybe. Yeah, that'll be a good place to stop. Trying to remember what's going to be in the homework next week. See, this page, using derivatives to find maxes and mins, that's where I'm talking about using it. And so it looks like, kind of thinking about this class, we'll probably get to that in the next period. Okay, let's talk real quick about higher order derivatives. So all that means is you can take more derivatives than just one. And maybe we haven't quite seen this yet, but all this really means is, so far, let me just go ahead and use the highlighter actually. Like it says in this paragraph right here, we're really just finding f prime so far, and I'm now seeing a typo. This should say f prime of x. Right, f with 1 apostrophe, and it means the first derivative. And we've also written it like this, d over dx of f, right? And so it's just worth pointing out, especially because we're going to start talking about the second derivative test and what the second derivative means. Note that you can take more than one derivative. And so let's say we had some function with derivative f prime, like we've been doing this entire time. The second derivative, notice how there's 2 apostrophes, is just taking the derivative of the derivative. I hate saying that word so many times, derivative. But that's what it is, right? That's what this is saying. It's saying, hey, if we do d over dx of something that's already a derivative, it just becomes the second derivative. Right? Maybe it's worth writing it down in words. So f double prime, you find that by taking the derivative of f prime. Right, so the second derivative you find from taking the first one. How do you think you get the third derivative? You take the derivative of the second one, right? So that's what it says in the second thing. You can find the third derivative by taking another one. And you can just keep going on forever and ever and ever, right? You can just you could take d over dx of f to the third, and that would be f to the fourth. And once we start getting past 4, we usually write Roman numerals up there. But you could just keep doing that forever. We usually stop at the second derivative in terms of implications and interpretations. Excuse me. But in some contexts, higher order derivatives have meaning. Folks, mostly what I'm trying to get across here is the notation, right? When you have another apostrophe, it just means you're doing another derivative, and you can just keep doing it forever. Is that okay? Any thoughts about that? So let's talk about the meaning. Yeah, let's do that real quick, and maybe this will clarify some of those things. And if not, we can come back to it. So let's say we have a function, f of x, right? Think about it meaning something. Maybe it's a population over time. Maybe it's the amount of money in your bank account, something that you care about, right? Well, we know that the derivative, f prime, tells us how f is changing, right? So Josh's question was, how do people use this in the real life? The derivative tells us how the function itself is changing. And so we've interpreted this a few times already. Let's think about it as a bank account, right? Everyone wants to have more money. If you have some function that tells you the amount of money in your bank account and the derivative is positive, you're making more money, right? Because that means it's increasing. If it's negative, something bad's happening and it's going down. And so maybe this is more an investment account or something like that, right? And so the first derivative tells you how the function is changing. That means the second derivative which we obtained by differentiating the first derivative, right? So and what I'm trying to say here is the relationship between the first and second derivative is the same as the first and the function, right? So what I'm writing right here, the second derivative tells us how the first derivative is changing.
But how would we be able to find how the first derivative is changing?
So we have a function, we differentiate that. So the question was, how do we figure out how the first derivative is changing? We have a function. If you take the derivative of that new derivative tells you how the function's changing. What I'm saying is, if you take a second derivative, it tells you how the first derivative is changing. And if we take another one, it just always relates back to the one before it in the same kind of way. And so one really easy example of this, to Josh's point, is if f of x is the position function, so it tells you how far you are from something, or you're driving from here to Worcester or something, right? And you have some distance function. Then f prime, what does f prime tell us then? What's the rate of change of position? What's another way to say that? Yeah, so f prime tells us how position is changing, which is velocity. Right, so if f is position, f prime would be how fast you're going, your rate of change, right? F double prime, which again is the differentiation of the derivative, it tells us how velocity is changing. What's another word for how velocity is changing? Acceleration, right? So acceleration tells us how, whether you're going to be going faster or slower. No, not necessarily. It tells us whether your rate of change is increasing or decreasing, right? So if you're accelerating, that would mean your second derivative is positive, which would mean your velocity is going up. Now these contexts are just in terms of like position, but we have similar relationships with other things too. So if it was like a population, then f prime would tell us whether population is going up or down, and then the second derivative would tell us whether or not that's getting faster or slower, whether the rate of change is getting faster or slower, I should say. I think that's really we're going to do a couple sort of specific examples and think about what those mean, but does that answer your question a little bit, Josh, about how this gets used a little bit? And the fourth derivative, I actually meant to look this up, I forgot. I think it's called, there's a word for fourth derivative that sometimes gets used. I'm not going to try to make it up. Ariana? Yeah, so we can write that down too, yeah. So then f to the third derivative would be how acceleration is changing. And there's a word for that. I can't remember what it is off the top of my head. Does anyone know what that word is? Called, people wanted to say torque, but it's not torque. All right, I'm gonna just look up one more thing. If this does it, great. It's the jerk. That's right. It's not the torque. It's called the jerk. So it's a measurement of acceleration changing. You can imagine if you jerk something, it's sort of thinking about acceleration. I don't know. It's called the jerk. I'm not even going to write that down because I'm pretty sure that's true. But anyway, most of the time, for the most part, we stop it at a couple derivatives. But it depends on the context, I guess, is the thing to think about. It depends on what we're talking about. Okay, so let's just do a quick example. How much room do I want here? I was hoping to have a little more room than this, but I think this is okay. So I'm just going to put a little line down the middle of the page and just do a couple examples. The first thing I just want to point out is that if you have a polynomial, so let's say f is 4x cubed, you can keep taking derivatives, but eventually it'll be zero, right? Because the power rule is just going to eventually make the powers go down to zero. And so just let's just do that real quick, right? So the first derivative would be 12x squared. The power got lower. The second derivative, 24x, right? The power got lower. Third derivative would be 24. Now we just have a constant. And so then the fourth derivative is just zero. And every other one is going to be zero too. And so the idea that eventually polynomials become zero is different than other functions, which sometimes get worse when you take derivatives. So in some sense, polynomials get better, quote unquote, or things get easier, or the function gets simpler at least, right? But there are situations where it just gets worse. So like, what about one like this, for example? Say we had just e to the x squared. Not even that bad of a function, right? Let's call that g. But if we do g prime, it's a chain rule. Okay, it's not horrible, right? But notice we won't do the details, but it ends up being this, right? And so the power comes down and multiplies, the derivative of the power, excuse me. But then if we try to take another derivative, then it gets worse because then it's a product rule and a chain rule, right? And I'll just write that one down real quick. So f prime g plus fg prime, right? So f prime g plus f g prime. Make sure that looks okay, yeah. And then if we did a third derivative, it'd be even worse because then it'd be, you have two terms, it'd be a chain rule, a product rule, and inside that second product rule is a chain rule. So it's just gonna like snowball and keep getting bigger and bigger and bigger. So the difference between like a complicated function and a polynomial definitely manifests himself in the derivative. Right? And again, if you think about what the derivative means, it's the rate of change. Polynomials are kind of simple. Something that looks like e to the x squared is a much more complicated looking graph. And so there's more complex derivatives. Okay, and we end up using the second derivative a lot kind of moving forward. If you look down a couple pages, we've got something called the second derivative test, concavity, the second derivative test, all this kind of stuff. We're going to be taking higher order derivatives. So that's why we're kind of introducing it right before we do that. All right, I'm going to stop there. Can I clarify something about higher order derivatives or the work on there? Again, I didn't write the details on those chain rules or anything like that, but. Here? Everyone online doing all right? Yep. Okay. So the next page is something we had already touched on. We already sort of jumped ahead and looked at the equation of the tangent line. And it was following these three steps. And I realized that that's a confusing thing for a lot of people. It's pretty standard or common for that to be a little confusing, but at some point we gotta nail down these three steps right here, like it says, and be able to do that. And we skipped over this example because it was a little premature to do. And so it's actually part of the example I just did a second ago, right? 2x e to the x squared. That was this example right here. And I actually already did the derivative, right? And so I'm just going to sort of give people a minute to think about this because this is one of the things that's in lots of the homework, but it's one of the things that people are really struggling with. And I feel like at this point, having done some homework, having looked at some product rules and all this kind of stuff, we should feel okay about a problem like this. So anyway, give this one a try. Let's remind ourselves how to do it. We're going to find the equation of the tangent line. Let me erase this part. Go away. So you find the derivative. Again, I just did it a second ago. You plug in the point we care about. At this point, The point we care about is x equals 1, right? Because it's g of 1. And then you use the point 1. The point is going to be 1 comma g of 1 to write the equation of a line. And I would just use the easy version of that equation. I would just do the y minus y1 equals slope times x minus x1. Let's just spend a few minutes trying these three things. There are the three steps. See what you can do. I'll sort of just wait a minute and then slowly start writing the answer down. Again, I just did the derivative on the previous page, so hopefully you have that. Just gonna slowly write it down if you want to check your work, but you really should kind of have a decent idea how to do this by now. So you take the derivative, product rule. It's the thing we just did a second ago. So write that down. That's not right. Just plug that number in. And I did this before, and so I plugged it into a calculator and got approximately 10.87 if you'd rather work with the decimal. All right, so that's the slope. All you have left to do is figure out the y value you need to use, right, which is just doing this, plugging in 1 into g, and then just put all the stuff into the point slope version of the line. Not too bad. I'm just going to pause there and let you think about that, and hopefully that'll help with some of the homework that's left for this evening. Can I clarify anything before I sort of slowly start writing this down? So the formula of the line there says we need a slope and we need a point. We have the slope, 10.87. We have the x value of the point, which is 1. We just need to figure out the y value, right? And so that's where plugging in the point comes in. So we plug in 1 into the original function. So it becomes 2e to the 1, which I also did ahead of time. Let me see, remind myself what that is. So that's approximately 5.4. And so that's your y value. So the point you're going to use is going to be the x value we're given, and then that corresponding y value. All right, so we've got the slope, we've got the x and the y, we just plug it into that function, And that's the end of it. So then the slope of the line is y minus the y value equals slope times x minus the x value, where it's just 1. That's what's called, and this is, I don't know if you guys are familiar with this one. I am used to y equals mx plus b. I feel like when I grew up, we hit y equals mx plus b hard. This is called point slope form. And it's one that doesn't get used as much as y equals mx plus b, but it's, in my opinion, a lot easier. You don't have to find the b. The other thing I'll point out is, because a lot of people seem to be struggling with finding the b. I've done a couple examples, a handful of examples of how to do that. I'll just point out, though, if you do the point slope form, you can just solve this equation for y, and that's another way to find y equals mx plus b form, right? So if you just take this and you just solve for y, just get y by itself, you could just translate this right into y equals mx plus b. Right? It'd be y equals 10.87x minus 10.87 plus 5.4, right? Just getting y by itself. And then that just looks like 10.87x. Let's see, I'm not going to do this math in my head, 5.47. So it's a nice, it's sort of a different way to get the b if you like thinking about it that way instead. Any sort of general questions? I feel like at this point, the homework that's due this evening should feel obtainable. Can I clarify anything from this section? All right. So let's see here. Doing well on time. I just want to introduce the next idea. I feel like if I just introduce this next concept, it'll make the next section go a little bit more smoothly. So I'm just going to probably run through this page. There's not really anything to write down here. We're going to add